Nope, I won't be doing that again.
I went to St. Louis to see Graham play, right? Well, he sat the bench, but like maybe he's gonna play maybe. The starting linemen, so there's like, I don't know, 5 of them, 6 of them, and the quarterback and like the starting wide receiver all got stuck in an elevator in like the student rec center, so they were late to the game.
That's so
It's
fantastic.
so scary. It is. I was like,
All right, chapter 4. Chapter 4 is about 2 things. One thing is solution stoic, and the other part is about redox. So we got kind of 2 parts going on here. Actually, we're going to skip part of chapter 4 all the way till unit 9 because it doesn't make sense to teach it right now. So if you're reading chapter 4, if you read it, the very end we're not going to do till later. But that's okay because that's how I want to teach it, and it's my class. So let's define a solution. How would you define a solution? What is a solution, usually? Not a trick question. Liquid, yeah, it's usually water-based, right? Majority of solutions are based on water. Why? Water is known as the universal solvent. Water is known as the universal solvent. What is a solvent? It dissolves the solute, yes. A solvent dissolves the solute. The solvent dissolves the solute. And why is water known as the universal solvent?
Molarity.
Yeah, you got it. Water is polar. Water is polar. It's a polar molecule. So a lot of times you'll hear in quotes like dissolves like. Okay, you may have heard that in former chemistry classes. Anyone ever heard like dissolves like in CP Chem? That is not going to get you points on the AP Chem test. Okay? That's like an immediate red flag. Okay? If they see like dissolves like, they basically assume that you didn't have a good teacher and like, yeah. You have to say why. Why does it dissolve? So let's just look at water. So let's just draw water. Here's hydrogen, here's oxygen, here's hydrogen. Oxygen has 2 lone pairs. We're going to bond these hydrogens to it. And hydrogen has what charge? +1. Because both of those wanted to give the one electron away they had, yes. And if oxygen is gaining 2, it has a charge of 2-. Agreed? If I split water in half right here, are there literally 2 poles? Do you see it? There's a negative side and there's a positive side. That's what a polar molecule is. You have a negative end and a positive end. The charge is not evenly distributed. A nonpolar molecule would have charge evenly distributed. But here I've got a negative side and a positive side. Head nod if you guys see that. I think that's one of the things that people don't understand, all right, what a polar molecule is. There's 2 sides. So why does water dissolve a lot of things? Well, a lot of things have charges, right? And if things have a charge, this side of water can grab what? And this side of the water can grab a? You got it. That's why water is the universal solvent, because it has 2 ends. So that's that. Okay. Then freshman year, you should have seen this chart if you took physical science. So here's A, here's B, here's C. We have solubility on the Y. We have temperature on the X. If you had me, you remember this was my Kool-Aid chart. Anybody remember that? My big Kool-Aid day? I juggled. Did I not juggle? Do you remember me juggling?
no, this is COVID.
Oh, shoot.
I had you.
What? Oh, I might have done lemonade.
That
Yeah.
was saturation.
That's it. That's that lemonade. Maybe I did lemonade. I don't remember. I didn't juggle for you guys freshman year? Okay.
No.
Well, that's okay.
Unfortunately.
Here's a solubility graph. Here's a solubility graph. Can I juggle for you now? I don't think I have any juggling balls, but that's okay. I got, here we go. Here's three things, okay?
Oh my god.
So here we go.
This
So I have
cannot be
two hands. My hands are the solvent, right? And this is my solute, all right? If I have this solute in this hand and I have a hand open, what would I be? I would be considered unsaturated. What would A, B, or C be unsaturated on this graph? C is unsaturated. So C is unsaturated. You could dissolve more at point C. If I have one in each hand, I can dissolve no more, I can dissolve no less. So now I am saturated. So which one's going to be saturated?
B.
B. This is really weird writing up the page. Have I done this before? And then the way I usually teach this freshman year is I'm like, here, Aaron. And I would say, throw the foot at me. Okay? Do it. What happened to the foot?
It did not go.
If I add too much sugar to my Kool-Aid, where does the sugar go?
To the bottom.
To the bottom. This is actually really dang good, okay? Stay with me. The only way to get more sugar is to do what? What do I have to add to the system? Energy, right? And what do I usually add energy as? Heat. So if Mira throws it to me again, okay, it's going to be hard with a foot. If I add heat, okay,
Oh.
I add energy,
No way.
now
Great.
I am what?
Crazy.
I'm super saturated now, right? I did not miss. That was pretty good. Okay? So a lot of people think when you throw the foot, right, you're super saturated. No, you aren't. You're just saturated with stuff sitting at the bottom. When you add the heat, though, guys, this is good. All right? When you add the heat, you're super saturated. Like it?
Yeah, that's good.
All right. So I just juggled a foot, by the way.
Aaron's having a good time.
People, when I post this on YouTube, it's just like you can't see that part. Anyways, so A is super saturated, and I didn't draw this super great because if it would have been accurate, A would have been probably at a higher temperature. It's usually a curve. It's fine. You guys get it. All right. But super saturated is when you add heat in and you can super saturate something. But the major misconception is that you super saturate Kool-Aid. No, you don't. Water can only hold so much. Cool? Okay. Kool-Aid, yes. Okay, we'll make a little chart. Can somebody grab the door? On this side, we're going to have dissolves easily. And on this side, we're going to have doesn't dissolve easily. Does that sound right?
Dissolves not.
Hardly dissolves.
Don't dissolve easily.
Yes.
You can write it however you want to, okay? So we have dissolve easily and don't dissolve easily. So let's talk about things that dissolve easily. This is going to be fairly new to you. The first things that like to dissolve easily are ionic solids. Ionic solids. Ionic solids are ions that have a positive and negative side, right? If they have a positive and negative side, they're going to dissolve really well in water. We're usually talking about water. Ionic solids is the first thing. The next thing that dissolve easily are strong acids. Put a star by this. This is one of the first things that you got to know, memorize for the rest of the year. You have to know what the strong acids are. Strong acids are hydrochloric, sulfuric, and let's also put nitric. Strong acids dissolve easily, and you have to know this, because strong acids completely dissociate. Strong acids completely dissociate. What do I mean by that? If I drop hydrochloric acid into water, it immediately breaks up into its ions, hydrogen and chlorine. All right? It breaks up. That's what strong acids do. That's why they're so strong. That's why they have such a low pH. We'll talk about pH later. But they immediately dissociate. Guess what else dissolves easily? Don't overthink it. Salt? Salt would be ionic solid. That'd be like sodium chloride. Strong acids dissociate, so strong bases, yeah. Strong bases. All right. Our strong bases are usually our alkali metal hydroxides. Are alkali metal hydroxides. So what would be an example of an alkali metal hydroxide? What?
Sodium hydroxide?
Lithium hydroxide, sodium hydroxide, potassium hydroxide. Those are the best examples. So lithium hydroxide, LiOH, sodium hydroxide, NaOH, potassium hydroxide, KOH. Because guess what these acids will do when they hit the water? Completely dissociate. They completely dissociate.
What is the last one?
KOH, potassium hydroxide. I would say that this area is really important to understand, all right? Because you have to understand this, and we're going to talk about weak acids over here, okay, for a lot of this to make sense. So that is dissolve easily. Things that don't dissolve easily are weak acids. So weak acids are pretty much everything else. So I'll give you a couple examples, like H3PO4. What would that be? Coke, right? H2CO3 is Pepsi, right? And these by themselves taste pretty sour.
No.
Yes, this is phosphoric acid, this is carbonic acid, but that's what you'll find in your pops. Notice how many hydrogens these have. This has 2, this has 3. Guess what these hydrogens want to do? They want to break off, they want to make water, right? What do they usually make water with? Oxygen and any other ions that they can have. What is it? What is the thing? I can't think of the name. Where you have like weak bones.
Osteoporosis.
Osteoporosis. Do you know that females tend to get osteoporosis more than males?
Yes.
Yes. It is scientifically proven that females get osteoporosis more than males. Guess what I think probably is going to be eventually discovered? One of the major problems of, or sources of getting osteoporosis is drinking pop,
No, it's drinking.
okay? Specifically, drinking your dark pops. Coke and Pepsi, yes.
Doesn't it like dissolve your teeth or something?
It's also not good for your teeth, because these are acids, right? Not good for your teeth either, you got it. But these are the pops that you want to stay away from. And guys, it's not great for you either, okay? But especially the ladies, it's scientifically proven that ladies have osteoporosis more than guys. So watch out for how much pop you drink. Another weak acid, this is probably one of the most important ones, is HC2H3O2. This is acetic acid.
Oh wait, I've seen that.
Which, yeah, you've seen it because this is vinegar. All right?
Yeah.
All right, vinegar, HC2H3O2. That's vinegar. That's a weak acid.
What does it say after
It's acetic acid or vinegar. Okay? Yes, this is phosphoric, this is carbonic. I'm just throwing a couple examples out there because everything else is weak acids, okay? And these do not completely dissociate. They more stay together when they mix with water. They make it more acidic, but they just break off little parts of it. So maybe you rip off just one hydrogen, or maybe you rip off a second hydrogen, but they don't completely break up. Now, our weak bases, so these are all sour. Our weak bases are like NH3 or NH4OH. Our weak bases are usually cleaners. So these are what you're going to usually find in cleaners. Bleach has OH in it. NH3 is what? Ammonia. Any farmers in here? Anybody here live on a farm? Anybody know what NH4OH is? Well, you know the name. NH4OH is ammonium hydroxide. This is what we use to fertilize our fields, right? If you ever see a farmer pulling a tank of something, it probably has a hazard. And it probably says like ammonia or something like that.
Do not drink.
Do not drink, right? And if you understand your chemistry, you really, as a farmer, it's probably one of the most important things to understand chemistry, okay? So this is a true story. There was a farmer pulling a tank. This is somewhere in Ohio. I don't remember where. Maybe Ironton, something like that. They were pulling a tank of NH4OH, and they were down in a dip, okay, of like a hill. And the NH4OH tank flipped, his tractor flipped, and it pinned him under the tractor. The NH4OH is leaking. Well, NH4OH as a gas is really dense. And this guy knew his chemistry, and he knew that the gas wasn't going to go anywhere. It was just going to pile up and suffocate him. But he had a pocket knife, and he was pinned under this tractor, his leg. He uses, this is like the climbing movie, but like a farmer part of it. He used his pocket knife, he sawed off the bottom of his leg. All right? He climbed up to the road and survived because he understood chemistry. Because NH4OH is super dense, the gas just sits there. If he wouldn't have got out of there, he would have suffocated. He probably wouldn't have died from being pinned under the tractor because he wasn't bleeding yet, but he would have suffocated from the NH4OH. So, what's that movie where he does he cut off his arm?
Yeah.
It's a climbing movie, 20-something hours, I don't know. 127 hours, yeah. It's like that, but farm version. So,
Dude, that's a more intense version.
The pain to go through
I know,
to cut.
you know, I would rather live.
Yeah.
I'd rather live. So, anyways, true story. True story. What would this look like? What would this look like? If I took a strong base, HNO3, and I added it to water, all right? I know that water is going to rip off a hydrogen. So this is going to make H3O+, which is called hydronium. Hydronium. It's the hydronium ion. You're going to have to know that. It's kind of fancy. Plus NO3-. And a lot of the times in chemistry, you're going to see later, as we get on through the year, there's parts we don't really care about. I don't really care about the water. You could see it just written as this. This would be the net ionic equation. HNO3 breaks up into just hydrogen plus nitrate. So that's a very simplified version. This would be the very basics of what's happening in this equation, which would be a net ionic equation, which is where we're going next with this. So where we're going next is, what is a net ionic equation? What are we going to do with it? You probably want to flip the page. All right? Flip your page, unless you have more than half a page. So we're going to talk about net ionic equations. And when you think of the word net, anybody here ever get a paycheck?
Yeah.
Okay. You've got a paycheck, you got two numbers. You got the gross and you got the net, right? The gross is the number that looks awesome. Yes? That's that big number before what? Taxes, union dues, your retirement, insurance. This is my real life, guys, okay? All of these things I've just seen to come out, okay? And then I finally look at what goes into PNC Bank, which is my net pay, right? What I'm netting. And it's depressing. No, it's kind of depressing to see it. Like when you see how much you could have got, well, how much you really made, and then how much you get, just like, ugh. Anyways, it's the same thing what we're going to be doing here. What we're basically going to be doing is going to write the gross equation. Okay, so imagine that as the gross equation. We're going to break that up into the different parts to insurance, and this is, just follow me. I've actually never done this analogy before, but I think it's going to work. We'll see. I just came up with this. I did. And we're going to see what does something. We'll see. All right? So we start out, step one, with a balanced equation. So step one is a balanced equation. So I'm going to write a balanced equation here. I've got AgNO3, which is AQ. That's aqueous. Aqueous means it's dissolvable. It's soluble in water. Plus NaCl. That's also aqueous or dissolves in water. What's that going to give me? That's AgNO3, AQ plus NaCl, AQ.
Ooh, that's a
What's that going to give me? It's double displacement. NaNO3, right? Is that going to be aqueous?
maybe.
Plus what? AgCl. Is that going to be aqueous? Get out your periodic table. Your periodic table, flip it to the back. A new section never talked about. Here are your solubility rules. I'm not going to write these out because for the most part we'll do it so many times that you're just going to get it. All right, and you know what's soluble. But your solubility rules. Most nitrates are soluble. Most salts containing the alkali metal ions are soluble. Most chloride, bromine, and iodides are soluble, except silver, lead, and mercury. Most sulfate salts are soluble, except those. Most hydroxide salts are only slightly soluble, which could be important in the lab next week. And then most sulfites, carbonates, chromates are only slightly soluble. I would say the important ones to understand and know on here are probably 1, 2, 3, and 4. You've got to know those, okay? You've got to know which one of those are soluble or not. These down here are more minor. But the solubility rules will tell you what is soluble or not in water. So, based on the solubility rules, is NaNO3 going to be AQ or what? It's soluble, because that is a nitrate salt. This is AQ. What about silver chloride? No. It's one of the exceptions. So the way I write that is solid. And a lot of times I like to write an arrow going down. Because what is this for my equation? The precipitate. That's my precipitate. So the way I figure out what my precipitate is going to be is from the solubility rules. So I'm just making a note there. I'm putting a liquid in a liquid, and I get a solid. This is what we're doing in lab next week. That's my balanced equation. Questions so far? Step 2 is the total ionic equation. So here's where I'm going to break it up into my insurance and all that stuff. We'll see if this works. I honestly don't know. So I'm going to break this up into anything that breaks up. Does AgNO3 break up?
Yes.
It's soluble, right? So this breaks up into Ag plus NO3 minus. Plus, does sodium chloride break up? Yes, it's soluble. Na plus Cl minus. Gives me, does this break up? Yep. Na plus NO3 minus. Plus, is my solid going to break up? No, I can't break that up. It's together. A reaction has happened. Plus AgCl. At this point, I need to determine what are my spectator ions. The spectator ions. The most basic definition are ions on both sides of the equation. These are things that are in my paycheck that don't matter for the end. They're just taking it away. So my spectator ions are NO3. You guys would agree NO3 is on both sides, yes? I like to box my spectator ions. That's why I put a box around the word spectator ions. That's a spectator ion. Do I have any other spectator ions? Sodium. This is a spectator ion. So in the total ionic equation, I break everything up and I figure out what my spectator ions are. Step 3 is my net ionic equation. I guarantee you, 120%, you will be writing a net ionic equation on the AP Chem test. Guarantee it. Every year. So my net ionic equation is what's left. So I've got Ag plus Cl minus yields AgCl. That's the net ionic equation. These are the ions that actually did something. That's what it is. Here's my net pay. I don't know, did that work? Kind of. All right. This is my net pay. These are the movers and shakers. So these were part, right? These are just floating in solution. We're going to talk more about that. These are just kind of leftover floating in solution, which means one of these must be what? Part of the, if they're just left over floating in solution, one of them must be excess. Oh, see where we're going with this? All right. One of those must be excess, right? And that's my net ionic equation. Okay, let's do another one. Let's do a weak acid example. So here's a weak acid. So if I have HC2H3O2, which is AQ, plus NaOH, which is AQ, gives me sodium acetate, so NaC2H3O2 plus what? This is AQ. Water. What is water going to be first state? Liquid. That's an L. Wow, that's a really bad L. Liquid. Water's a liquid. Water's not going to break up. It's water. So I made water. There's my balanced equation. Next step is write my total ionic. Is this first one going to break up?
Yes.
No. It's a weak acid. This is why you have to understand the difference between a strong acid and a weak acid. The weak acid is not going to break up, which is why I'm doing this example. So I have still acetic acid, so HC2H3O2, plus sodium hydroxide will break up, right?
Yes.
Plus Na plus OH minus yields sodium acetate, that'll break up, Na plus C2H3O2 minus, water's going to stay together, plus H2O. Plus H2O. Yes, Marin?
So whenever we're listing out the strong acids, those are the only strong acids?
I think those are the main ones that you have to worry about.
Okay.
So at least in this chapter, I think that I'll look it up
Okay.
and make sure there might be a couple other, but yeah. What are my spectator ions? Sodium is my spectator ion. That's not doing much. So my net is going to be HC2H3O2 plus OH minus yields C2H3O2 minus plus water. And when you look at this, you should be able to tell what actually happened. What did hydroxide do to acetic acid? It took away a hydrogen, which made water and left. This tells you the story. This tells you the story of what actually happened. Also, this will always be balanced at the end. It also always has to be reduced. The examples I'm doing today are all 1, 1, 1, 1. But let's say there was 2 NaOH here. This would have been 2 Na plus 2 OH minus. So as you're working through those problems in the book, don't forget that. You'll never end up with 2, 2, 2 in the net ionic equation, or 2, 6, 4. If you end up with 2, 6, 4, guess what you have to do? Reduce. And it does balance every time. You ready to try one on your own?
Yes.
Here we go. So let's do HCl plus NaOH. Write the products and figure out the net ionic equation. And when you get good at these, eventually it's like, boom, I already know. I know what it is from looking at this, what the net ionic equation is. HCl, AQ, NaOH, AQ. Whenever you have an acid-base reaction, you always produce a salt and water. Did you make a salt and water?
Yeah.
Did you literally make salt and water?
Yeah.
Okay. So I have NaCl, AQ plus water, which is a liquid. Okay. Get to your net, your total on your net. Does HCl break up?
Yeah.
Why? Completely dissociates. H plus Cl minus plus Na plus OH minus gives me Na plus Cl minus plus water. There's my total. Spectators are chlorine and sodium. Does your net make sense? Hydrogen plus hydroxide makes water. This will be the net ionic equation in a whole bunch of reactions that you do next week. All right? And whenever it's acid-base, it's almost always this. If it's a strong acid, strong base, it is always this. Okay? It is always this. Last thing I want to do, well, a couple more things we can do, is define molarity. So molarity, M-O-L-A-R-I-T-Y, is symbolized by a capital letter M, because lowercase m is mass, is number of moles of solute over liters of solution. Number of moles of solute over liters of solution. So this is our new part of Stoich, because we can work in liters now as well. What I want to do is set up our first example for tomorrow, then we'll call it a day. Okay? How much space do you have left in your paper? If it's less than half, I'd flip it. It's going to be a lot of work. So here's our setup for tomorrow. 24.3 milliliters of 0.200 molar lead 2 iodide Oh, wrong. Lead 2 nitrate. That's not going to be soluble. Lead 2 nitrate react with 36.7 milliliters of 0.250 molar sodium iodide. ... I could ask you, how much lead 2 iodide precipitate is formed in grams? So we're taking our knowledge from last chapter. So we know tomorrow the first we're going to do is figure out what? The balanced equation, and then we have to figure out what? We're doing no net stuff here. All right, we're just back to our regular stoic. We're moved on from net ionic equations. The next step would be figuring out the limiting reactant, right? Lead 2 iodide precipitate, PPT, is formed in grams. So this is taking what we did last chapter. This is why chemistry just keeps building, guys. If you don't understand what we did last chapter, you got to come talk, because it's just going to keep building and building and building. So tomorrow we'll leave off at this point.
Is that lead 2 nitrate or nitrite?
That's lead 2 nitrate. Nitrate. Lead 2 nitrate. So tomorrow this is where we'll leave off.
That is